Hello! Last time, we discussed stable outcomes in the network bargaining game. The idea is that if everyone receives a payoff that is at least their outside option, then no one would be willing to defect from their current matching. However, a stable outcome might not reflect real-life experimental results. Take a look at this example where 4 players form a path, and there is value 1 on each edge. The outcome where the matching edges are AB and CD, and everybody receives a payoff of 1/2, is a stable outcome. You can check that the outside options are 0, 1/2, 1/2, and 0, and these values are less than or equal to the payoffs. Now, even though this is a stable outcome, in experiments, B and C tend to get more than A and D. And that is because A and D have no other options, but B and C do have alternatives. So B and C should get more, but how much more? Let's recall an idea from Nash's bargaining solution. In a matched pair, each player take at least the outside option and split the rest. In other words, after deducting their outside options, they are equal. So this gives us the following definition. An outcome mx is balanced if xu minus alpha u is equal to xv minus alpha v for all uv in the matching M. In our example of the path, one possible balanced outcome is 1/3 for A and D and 2/3 for B and C. We can check that the outside options are 0 for A and D and 1/3 for B and C. And for an edge in the matching, say AB, reducing the outside options from its payoffs will leave us with the same number, 1/3. So this is a balanced outcome. Here is another graph with all the edge weights 1. Try to see if you can come up with a balanced outcome here. The maximum matching is AB and CD. If we assign the payoffs to be 1/4, 3/4, and 1/2, 1/2, the outside options are 0, 1/2, 1/4, and 1/4. And you can check that this is a balanced outcome. As you might expect, player B is in a more powerful position here. They get the highest payoff. Now you might have discovered that finding a balanced outcome is harder than finding a stable outcome. So the question is, do they exist and how do we find one? Unfortunately, we are not going to go through the entire theory of balanced outcomes here. We can only provide a summary of known results without proofs. The first theorem is that a network bargaining game has a balanced outcome if and only if it has a stable outcome. So the condition for the existence of a balanced outcome is the same as the conditions for the existence of a stable outcome. Note that it is not hard to prove that balanced outcomes are stable. We now look at an interesting structural result for network bargaining games where all the edge weights are 1s. But first, we need to make a definition. A vertex V in a graph G is inessential if there exists a maximum matching in G that does not use V. For example, in this path with 3 vertices, there are 2 maximum matchings. In the first one, C is not used. In the second one, A is not used. So A and C are inessential. For a cycle of length 5, a maximum matching has size 2. This leaves one vertex out of the matching, and it is inessential. By symmetry, this means that every vertex is inessential. And here is a theorem from Kleinberg and Tardish. In a graph G with weight 1 for each edge, the following are equivalent. There is a stable outcome, there is a balanced outcome, and no two inessential vertices are adjacent. For example, looking at this graph here, the bow tie, can you tell me what are the inessential vertices of this graph? There are 4 inessential vertices in this graph based on 4 different maximum matchings. We see that 2 of them are adjacent, so no balanced outcomes exist in this graph. In the example of a path with 5 vertices, the inessential vertices are on the 2 ends and in the middle. They are not adjacent, so balanced outcomes do exist. As an aside, if you have taken the graph theory course, the set of inessential vertices is the set D in the Galai-Edmonds structure theorem. And the condition that no 2 of them are adjacent means that D is an independent set. If we move towards the general weighted network bargaining game, then we do not have such a nice structural result. But there is an efficient algorithm for solving it. So here is another theorem by Kleinberg and Tardish. If a network bargaining game has a balanced outcome, then the balanced outcome must use the maximum weight matching, and there exists a polynomial time algorithm for finding a balanced outcome. Note that a maximum weight matching might not be a matching with maximum number of edges. In this example, a balanced outcome involves the edges of a maximum weight matching, which is just a single edge in the middle. But a maximum size matching has 2 edges. And here is a balanced outcome. I'll leave you to check that this is indeed a balanced outcome. Now, if you're interested in the proofs of these results by Kleinberg and Tardish, their paper on the network bargaining game is referenced on Learn. And that concludes our discussion on cooperative game theory in this course.